Okay, good evening everybody. I hope everybody's having a wonderful day. So today I'm going to be talking about stacks and queues. Now, we've already actually talked quite a bit already about stacks. So you're going to find I'm not going to say as many things about stacks today, but I'll focus a bit more on this other data structure or this thing called a queue. So I'll talk about both of these today, and depending on how far along we get, we might start talking about sorting algorithms. So before I get into talking about what a stack and a queue, like what these things are, I've got to talk about some terminology. So the first thing is that sometimes people refer to something called a container. This is just simply a data structure that stores a collection of elements. So for example, a stack would be one because it contains a bunch of elements. But the thing is, the way we insert and remove elements from this container differs. From, say, for example, when I just have an array, for example, I can do all sorts of things with that kind of container, right? Because an array technically is a data structure that stores a collection of elements as well. So we can have many different kinds of containers. So we'll see a lot of different kinds of containers in this class. So stacks and queues, the reason why I want to kind of lump these two together is that they're used for representing and performing basic mechanisms or modeling for certain processes. So you might say, Dan, that sounds like that sounds really vague. And it is quite vague because there's a lot of processes that operate like these things. So it's a broad class of processes you can model with stacks and queues. So we already talked about what a stack is. Actually, we talked about it quite early on in this class. But just to remind you, we actually had some rules for how we inserted and removed data from or removed our elements from this container, right? So we used this so-called LIFO or last in, first out rule for our stack. Now, some examples of stacks where you can encounter these. This isn't by any means a complete list. Some ways you might encounter a stack, for example, we talked about the call stack. That's memory management on behalf of the system. For example, how it manages function calls. For example, if we're trying to perform some kind of search, retracing steps that you make in that search. For example, say if we're talking about the assignment, if you're thinking about how the stack gets used in this case, it is used to retrace steps, almost like you're remembering things. Now, another way you can use a stack, this is one way I find that's pretty helpful to visualize, is as an undo feature. So recall that we had a stack. We talked about this at the beginning of the class, so let me just kind of give you an idea of what I mean by an undo feature. So when you have a piece of software, say for example like a text editor or a word processor, you may perform a series of actions, a sequence of actions. For example, you could be like that you type, you type Z, and then you press space, and then you performed a copy, like you might Control-C or something like that. And you could record all of these actions, for example, in your software. And, suppose that you accidentally typed the wrong keystroke. You type O, for example. And you want to undo this process. Well, if you keep a stack around of a fixed size, you can have it so that your program can remember the actions that you have taken up to some point. This is, for example, like some pieces of software, you'll notice that the stack actually, whenever you do undo operations, it only goes to some point. Like it goes down to maybe like, it depends on really how robust your word processor is. But it may go down to like 16 undos. It may be like 8. I'm not quite sure. But the point is that you can implement an undo feature using a stack. For example, if you were to go Control-Z or something in, say, like a word processor or something like that, what you could do is you could pop off this operation. So what you said here is, okay, type O. Well, what this could be is that every time you do one of these, you have whatever's the opposite of that occur. So for example, instead of typing O is, you want to return the software to a state where you don't type O. And you can pop that off the stack. And then if you wanted to have it where before you do a copy, you can uncopy that. That's kind of weird. But the point is that you could use the stack to remember your previous actions. So does everybody get the idea what I mean by an undo feature? So this is one way you could use a stack, for example. And of course, I talked about the analogy of a stack of plates, which is a natural way of thinking about this. So I have a stack of plates, and I could push a stack. Sorry, I could push a plate onto the top of the stack. I could pop it off the stack. I could also take a peek at the top of the stack. I could figure out how many there are in here. I could tell you if there are no plates. So these are just some examples of ways that stacks may occur. Now, the other one that we're going to talk about is a queue. Now, it follows, if we're talking about insertions and removals of our container, it follows FIFO rules, first in, first out. And you actually are probably quite familiar with this process already. You encounter it quite often in daily life. For example, if you find yourself waiting in a line to be served, this is an example of a queue. Queuing processes occur all the time on computers. So that's why I just kind of put it in air quotes. These processes are all over the place. So for example, if you have, so you may have heard of the concept of buffering or a buffer. Queuing has a close relationship with buffering. But the point is that the queues occur all over the place. You already have seen what a queue is before if you've waited ever in a line. So are there any questions yet so far? So just remember these two rules. So LIFO, think of that for the stack, and FIFO is going to be for the queue. So we're going to see how these are going to play out today. So one other piece that I want to add to this is an important assumption I'm going to make in this lecture. So whenever I talk about an implementation of one of these data structures, and I use an array, so this is going to be an assumption I'm going to make in this lecture. I'll address it if we have time after. An assumption is that array-based implementations have a capacity which I'll call capital N. So this will be a number that is going to be predetermined, and this will be something that of practical consideration. So in practice, you would try to figure out what exactly this capital N might be for your application. Now, if you don't know it, if we end up having an array and we run out of space in our array, what do we have to do? So what do we have to do if the array gets full? So any ideas? What should I do? So remember, I don't want to empty it because I want to hang on to everything that's in that array, but I might need I need more space. So any suggestions of what I could do? Yeah, you could dynamically resize the array. For example, you could take your array, you can allocate a brand new heap. Sorry, not a heap, an array. Sorry, I was looking at the chat. Yeah, this would be something that you would allocate. So you'd allocate a new array, and you can make it of a larger size that's big enough to fit whatever rest of data that you would like to fit in, until perhaps that might get full as well. And you copy over all of your elements from your array, and then you could reassign whatever your array is to the new array, and you could delete the old one. So I must stress that I will be giving you some code that shows you how you could do this if you've never seen this process before. So it'll actually be in the example for one of these implementations. So just keep in mind that in practice, very often you'll know what this N is, or this will be something that you try to figure out. But I must stress that all of these data structures will operate if it's an array-based one. It doesn't matter if this N is known or unknown. Just one thing that you have to be keeping in your mind is that most generally, it's typical that I won't be able to assume that the array is always going to be at most this number that I don't know about sometimes. So that's just something I want you to just be aware of. It's going to have some capacity. And that also will be the initial length of the array. So, anyways, let's start talking about stacks. So most of this, you're going to feel like I've already just talked about it actually a while back. Let me get the... Excellent. So let's start talking about stacks. So just to remind you, I got to remind you what a stack is, because we talked about what a stack is much earlier on. So just remember that you can imagine like a stack of plates. So suppose this is C, this is B, this is A, this is the top of the stack. So you can imagine it like a stack of plates, for example. So what did we define as a stack? Remember, it's an abstract data type. So remember, it's an abstract data type. It's a container. So it is a container. So is a container. That follows LIFO rules for insertion and removal, it's a little squeaky, removal of objects. So whenever we want to place an object onto the stack, we could use a push operation. If we don't want to remove something from the stack, we use a pop operation, right? But there's more operations than just those for the stack. So let's talk a little bit about those. So let me just define those operations. So I'll say it supports. So remember, I'm telling you the what right now. So remember, I have push. So push. So this looks like something I wrote previously. Adds an element E to the top of the stack. To the top of the stack. We have pop. This, of course, removes and returns the top element from the stack. And of course, or null if the stack is empty. So this shouldn't be anything too surprising, right? We've already talked about these two operations already. So there's some other ones, and if you're thinking about these things already, you should probably have already seen some of these already. For example, peek, you just simply return the top element of the stack. And of course, this is or null if empty, right? Now, I must stress that some people may give you a variant of this ADT where instead of returning null, it reports an error. Some people define the stack ADT to do this as well, and that's perfectly fine. This is just one way of defining the stack. So for peeking, remember in peek, we don't remove the top element. We just keep it there. Remember, I just want to inspect it. I'm just going to put it like eye level like this, and I'm just staring at it. And I could get the information I need. I could inspect the top of the stack. Now, of course, we have some other ones. We have size. So this tells us so you just simply return the number of elements. And of course, there's is empty. Which, of course, returns whether the stack is empty or not. I'm sure the name of it kind of gives it away. Is empty or not. So true or false. So these are the functions that I would want, or methods of a stack. So if I can implement all of these operations and represent it this way, then I can call what I have a stack. So as long as I have all these operations and they behave like this, that is indeed a stack. So are there any questions before I proceed to talk about ways to implement a stack? So keep in mind, we already actually talked about one of them, but I will briefly touch upon it. Okay, so let's proceed. So let's talk a little bit about this. Let's talk about stacks. Okay, so the first implementation I'm going to talk about is one we have not talked about yet. It's involving an array-based implementation of a stack. So I'll refer to this. I'll refer to this as array stack. So this will be the first of the two ways that you can implement a stack. I'm just going to refer to it as an array stack. So I must stress that I have in the notes full code for this one, because I want you to be able to see at least one of these array-based implementations of a stack or a queue. Because once you see one of them, it's not very hard to translate it into the other. So for example, if I gave you an array-based version of a stack, it's not very hard to see how to translate it to something that's an array-based queue, for example. Just there's some small little details you have to pay attention to. So I'll say C++ in the notes. But let me talk about this. So we maintain an array, and I'll call it stack. So that's its name. So that's the name of it. I'm just going to call it stack with some capacity. There's a lot of excitement. With some capacity. So remember, this is that capacity I was talking about. So this would be the initial value or length of the array. To store elements. So what we're going to do is we're going to have a counter called top, so that if we add 1 to it, we get the number of elements. So you might ask, Dan, why would you do it that way? Like, wouldn't you have just like we talked about this, like it makes a lot of sense to just have a variable that you keep a count of. You're gonna see how this counter gets used in our array. So let me let me just finish up my thought about this top here. So I'll say at the beginning. So when you initialize this array-based stack, at the beginning, set top to -1, meaning it is empty. So whenever the stack is empty, top is going to be equal to -1. Why? Because if you add 1 to it, it tells you that the number of elements is 0. So let me show you this nifty thing I could do with this top now. So I'm going to draw a fun picture, and I'm going to explain all the operations using this picture. I'll include in the notes descriptions of what I'm going to walk us through here, because I think it's more important that you see how it operates as opposed to just jotting down a description, which you can always look at in the notes. So let's see here. So imagine I have an array. So now remember, my array, I'm going to call it stack. So some points I will make. So let's talk about each one of these operations. So I'm just going to imagine I have just a whole bunch of elements here. And it starts off 0, 1, 2, 3, goes all the way up to capital N minus 1. Now, suppose I have this array. There's a lot of elements that could be in here in between, right? But I have a question for you. If I wanted to do this, if I wanted to push, for example, an element into the stack, is there any suggestions of where I should stick the first element? Any suggestions at all? Yeah, position 0 seems really natural, right? So now you might say, okay, Dan, so what are we going to do? So what we're going to do is we're going to increment top. So let's increment top because we're going to put a new element in. So keep in mind that prior to this, top is -1. What I'm going to do is I'm going to increase top by 1. So now it's 0. And I'm going to place, so let's keep a picture here just to keep us a little bit in mind what we're doing here. Suppose I pushed in an element and say, I just called it A, for example. So we're going to increase top by 1. And we're going to place it right here. So the neat thing about top is that the way you know about where to put it is it's always going to be stack sub top. So when you're doing a push operation, you increase top, then you just assign it into the spot for which it is currently telling you where top is. So notice that I don't have to do anything very complicated here. It's really nice and simple. So just to walk us through this process again, suppose I wanted to push another element, say I call it B. What would I do here? So let's walk through this process. So where should it go? Where should B go? Yeah, position 1, because what I do in my push operations, I'm going to increase top by 1. And then I'm going to insert B in stack sub top, which is position 1. So do you see how, whoops, I'm losing my friends here as I'm kicking things. That's pretty epic. So anyways, we got ourselves a couple elements in here. Now you could keep filling in this. So for simplicity, I'm just going to kind of suppose that I have all of these with elements in them. So keep in mind that every time I perform one of these insertions by a push, how could I access the top of the stack? So where is the top of the stack in this array? So where is the top of the stack? Suppose I have, so tell me what I could use to tell me where the top of the stack is. So suppose there's a whole bunch of elements that I pushed, and I don't know, suppose that I pushed another element, say, we'll call it Z. And you know Z will go right here. So what would this be? Like, what would it be? Where's Z? Now keep in mind, the answer is not, I'm not looking for N-2. Yes, it's top, exactly. We could use top. So keep in mind that the current top of the stack is whatever's indexing top. So if I just look at top, it tells me the number. So in this case, if we were to look at it, it would be whatever N-2 is. And I could index into that spot. So if ever I want to do a peek operation, or if I want to do a pop operation, I know exactly where the top of the stack is. So notice that every time I'm doing this, I know exactly where the top of the stack is in the array. Does everybody see that? It's always going to be at top. Remember, top is just a number that keeps track of the position in the stack as I push. So likewise, the nice thing about this is if ever I want to figure out the size, so if ever I want to figure out what the size of this is, like I said up here, The size is always top plus 1. So you can easily just implement the size method by just simply adding 1 to top. Isn't that easy peasy stuff? Like it's really nice. It's a really nice, simple, but effective way of implementing a stack. So if you know, for example, what this n is, you could keep this going like this, and it's nice. Actually, it's quite effective because keep in mind that if this isn't too big, using an array like this is rather effective for all these operations because I can access any one of these spots very quickly. I don't have to do any fancy stuff. It's very simple. So you might ask, okay, Dan, so what do we do when we want to do a pop then? So we know where the top is, right? So I could just get this right away from what top is. So if I want the top of the stack, the top of the stack is just stack sub top, right? Like I said previously. So, any suggestions of how I'm going to perform the pop? Any suggestions at all? Yeah, so we could retrieve this, so we could get this for our element. Then we could just decrement top by 1. That's really simple, right? And that, believe it or not, that's all there is to the pop method other than just simply returning whatever the element is. It's very nice and simple. It's one of the nice things about using an array like this. So that's all I have to really say about the array-based implementation of a stack. Are there any questions about the array-based implementation of a stack? So like I said, in the notes, I will have descriptions of all of these. So all of these, everything I just said in words will be in the notes. So if you ever find yourself watching this in the future or come back to this, or if you just want to take a peek at the notes, it's like, oh, that's what Dan was talking about. It's really straightforward. But like I said, if you want to play around with this array-based version of a stack, I have all the C++ code. It will be in the notes. So you can play around with this guy. So, some things I want to point out, again, like I said, if you know what n is, this guy right here, if you know what n is, this implementation is very effective, assuming that n isn't massive. Because remember, if you allocated an array that had like millions of elements, that takes up a lot of space, and you may want to do some other things too. So, keep in mind that consideration of what that n is. Likewise, if you don't know what n is, you're going to have to resize this array. But that isn't necessarily a hindrance towards the implementation. There are simple ways to take care of that, which I'll address a little bit later on when we talk about the time complexities. So let's talk about another implementation. So I must stress, this one I don't have as many things to talk about because there's 2 reasons why. The first one is I've already actually talked about this implementation previously. But likewise, I've already, you're playing around with this actually. So let me just talk a little bit about that. Let's talk a little bit about this. So for those that are working away on this, you might be like, Dan, this seems awfully familiar. It's because it is. So let's talk about it. But like I said, you still have everything I've told you in the assignment is just as much as I told you previously. So here's another implementation is the link stack. This should ring bells in your ears. But keep in mind, I'm not going to tell you what to do with the C++ here. So I want to show you that array-based implementation so you can see what you would do with an array-based version of this. This one, however, you're having some fun doing this one. So anyways, we talked actually about this before, so I'm just going to point out. So for anybody that's looking at your notes, say if you're looking at your notes in the future and you're studying, you're like, Why is there not a whole lot written here? It's just to remind you that we talked about this already. We talked about it already, but I just want to walk us through just a general idea of this implementation. So we're going to have nodes. So this is a linked list. Linked list where the top is in, so where the top is in a node at the head of the linked list. So keep in mind that top is actually a pointer to the node. I just feel like I need to address where exactly the top is from the most abstract sense of the plate of the linked list. And then of course we have a counter. So we have a counter called count to keep track of the number of elements. So let's talk a little bit about this. So I'm going to draw us out a picture. So just as a reminder, this is in fact going to be using a linked list. So we're going to be using what is called a singly linked list. There's another version called a doubly linked list. We may talk about these a little bit later on in this class. So remember that each node will have a data attribute and a next attribute. And the element is going to be in here. So that's where your element, so it's going to be probably a pointer to some object in here. Or it might be just simply we're just going to be putting stuff right in here. The point is that we have our data, which is going to consist of the element. And when we start off our link stack, I must stress that the initial setup will look like this. Top is pointing at null, and count is equal to 0. So that's the initial setup of this linked list based implementation. So as we push operations, we're going to insert nodes at the head of this linked list, which the head is top. So, for example, let me just draw you a picture of what this might look like after some push operations. So you might recognize this picture from earlier in the course. So we got A, B, C, D. This is top is pointing to the head of the linked list, which in this case is pointing at this node that has as its element, its data, is A. And this naturally corresponds to a stack that looks like this, where the top of the stack is A, B, C, and D like this. So question. So a lot of these are going to be really, the one thing I really like about this implementation, just to give you my thoughts about it, is I think that if you understand how a linked list operates, you know how this is going to work. So I have a question for you. If I wanted to implement the size function, what would I do? So could somebody tell me what does the size function do for my link stack? So what does it all have to do? That's it. Just tell me. What does it do? It just returns my count, right? Because remember, I have a counter. So every time I push, I'm going to increase this counter. Whenever I pop, I decrease this counter. So for example, in my picture here, the number of elements is 4, so count would be 4. So whenever I do a push, I'll increase the counter. Whenever I pop, I decrement the counter. If I want to know the size, I just simply return whatever this count is. Whenever I want to check if the stack is empty or not, it's really easy. I just evaluate whether this is in fact 0 or not, right? But beyond that, all it is for pushes. I'm just inserting a new node at the head of this linked list. Just a couple of tips. Just remember the order in which you perform pointer assignments. For example, you'll create a new node. You'll make the next attribute whatever top is, and then you would update what top is to be your node. Likewise, if you're doing pops, make sure you're removing from the head of the linked list. For example, let me just draw you an example. If I did the pop on this, what I would do is I would want to make sure I get back A, right? Remember, whenever I want to do a peek, I could just retrieve that from looking right at the whatever top's data is, because it's pointing right at the head here. So I would just want to hang on to this. I would use this information to tell me where the next node is, if it exists. Now keep in mind, one warning I have to give you is that you need to make sure you hang on to this node if you need to delete it. So if you delete it, you need to make sure you have a pointer to this node at some point. So you maybe give this a name. That's one thing to keep in mind. Other than that, you would, of course, when you're done with this, you can get rid of this node. But remember, just return back the element. And of course, decrement your counter. But yeah, no. So are there any questions about the link stack implementation? Any questions at all? There's not a whole lot really I have to say about this one. We've talked a little bit about this before. So if you understand how a linked list works, you'll understand how this works. It's really not nothing too beyond that. So I want to talk briefly about other things you can do with a stack. So let's head over here. So I just want to bring up a couple of interesting properties stacks have. And I want you just to keep these ideas maybe in the back of your mind. If you ever think about, hey, could I use a stack to do that? There's several different ways you can use stacks, as I showed you. But there's a couple of interesting things you can do with them because of the structure of a stack. So I just want to point out a couple of quick things. Is we can use a stack for other applications. So I want to draw you a fun picture. So suppose I have an array. I don't know, I call it A. Suppose I have an array A. And it has some numbers in it, like, I don't know, 3, 5, 7, and 8. And suppose I have a stack. I don't know. I'll just call it stack, just to keep it simple. Now, what I'm going to do is I'm going to push each one of these numbers as elements into my stack. So I'm going to push 3, then I'm going to push 5, then I'm going to push 7, then I'm going to push 8. Now I want you to think about this. If I pop the elements from this stack until the stack is empty, what order am I given these elements from the stack? I see it in the chat. Yes, exactly. So instead of having it back in 3, 5, 7, 8, you actually get it all in reversed. So that's an important property I want you to be aware of about a stack. So if you find yourself ever meddling around with collections or containers, and you ever want to reverse data in it, you can use a stack to achieve this by you just dump them all by pushing them onto the stack, and you can always pop them out. That's one thing I want you to be aware of, is that so if you pop all of these, it comes out in reverse. This is because of the LIFO. the LIFO policy that a stack has. So just keep in mind, so if a collection of elements are pushed onto a stack, then each is popped. So let me reiterate. If a collection of elements are pushed onto a stack, then each is popped. The order elements are returned is reversed. So if you ever find yourself in a predicament where you're like, okay, I need this, but I need it the other way around, you don't have to, for example, like, keep in mind that I'm just saying any collection of elements. If you have a more specialized structure that makes it a little easier to do this, you most certainly can do it that way. I'm just mentioning that you can use a stack in a very general way to achieve this process. So that's one thing I want you to keep in mind. Another one that you can do with a stack that you may see in the future on a lab is you can pair elements that are enclosed. So, for example, what I mean by this is that very often we encounter mathematical, the M word, mathematical entities or even semantic qualities that we may format in data. For example, parentheses, or for example, if we want to talk about, say HTML tags. Now, for those that are not familiar with HTML tags or parentheses. Now, for those that aren't familiar with HTML, very much the idea is that you have tags. In fact, another example might even be XML. XML, if you've ever seen XML. Either way, these are things I just want you to be aware of. I won't test you on that, but I most certainly want you to just be aware of it. Is that very much HTML is encoded using so-called groupings of tags, where you have, say, for example, the things that get displayed on your web page, for example. There's several aspects of an HTML file. One is, for example, the body, and it has a tag called body, and at the enclosure at the end of the body, so wherever you describe all the stuff involving the body of the website, it has a closing tag for the body. So what I would like to have is some way that I can make sure that there's an opening tag and a closing tag for every part of my script. You can use stacks to achieve this by just simply dumping in every time you have an open tag or an open parenthesis into the stack, and then whenever you're expecting that symbol, you can pop it off when you encounter it. But yeah, you'll see an example of this later on in this course, okay? So I just wanted to show you, just give you a couple of interesting ways you can use stacks. So are there any questions about these two? I just thought I would bring these up. I like to give you some ideas of what you could do with these. One thing I'll mention is that if you find yourself saying, I want to try doing this first one, I do actually have code in the notes if you want to, say, reverse an array using a stack. So if you could just take a look in the notes if you want to see what a function like that would look like. So that's all I have to say about stacks. Are there any questions about stacks? If we're all good, give me 2 thumbs up. Okay. So let's proceed. Let's start talking about queues. So now queues, they're sort of like like if there's if there was ever like a buddy cop movie, like the stack and the queue would be like the buddy cops. So you're going to see that these two are very similar. So I won't have as many things to say about it because most of the things that you're familiar with from a stack just sort of carry over. It's just that just the rules change a little bit, and we'll have to take those into consideration. But the overall idea is very similar. Exactly, right on cue. So let's talk about cues. So just simply imagine a waiting line. Imagine a waiting line with a front, with a front and a back. So imagine you show up to your local coffee shop and you're going there to get your favorite drink. Now, I brought the whole crew with me, and they're all just, they say my friends all got there before me. So when I show up to the coffee shop, I gotta wait at the back of the line while all my other friends wait here in the line. So my lovely green friend here is at the front of the line, and I'm at the back of the line. Now, naturally, if I'm at the coffee shop or something like that, I don't really drink coffee, but I know a lot of people do. But I get a fun drink anyways. So my lovely green friend here, since my lovely green friend is at the front of the line, what will happen is when my lovely green friend is getting served and is done, my lovely green friend leaves the line with the favorite drink. So the next person would be this lovely horse here. This lovely, lovely horse. But the whole idea here, and you know what this is like, right? You've done this probably several times in your life where you're waiting in a line to get served something. That's what a queue is. A queue has a rear and a front. So I'll refer to the back as a rear. I'm not talking about the horse's rear. I'm just talking about the rear of the line. I love that comment. Oh, it's wonderful. Yeah, no, there is actually other data structures that you can model things just like that. Depending on how much time we have in this class, I may talk about them. They're called priority queues. I could do something like that with that. But I know for sure you'll see that in 340. Not necessarily that scenario, though. So just keep in mind that there's a line. And say I have my friends or anybody else that wants to come to the coffee shop. So this would be the front of the queue. And this is the back of the queue. So this person here was the one that just entered. This is the most recent person that entered in. And we call this FIFO, first in, first out, because when you're the first in, you're going to be the first one that leaves. It's like first come, first serve, right? So the waiting line, so if you think of this as a waiting line, so our waiting line, this would be the queue. And what happens is when I'm done with, say, a person, or in this case, these people represent elements. So when I'm done with them, I dequeue them out. I dequeue out these people from the front. And I'm going to enqueue. I'm going to enqueue in people from the back or the rear. So I'm going to call back rear because I'll very often call it the rear when we start talking about implementations. I just was thinking about the horse thing, and I was like, should I write back or rear? I'll leave it as rear. So anyways, so does everybody get the general idea of what a queue is? You've probably experienced this before in your life. Sitting in a line waiting to get something. So the idea is that we can DQ them off the line and we can NQ them in. Now, if you don't like the words DQ and NQ, another phrase that you can use is leave and enter. If you don't really like that terminology of DQ and NQ. So let's talk about the QADT, everybody. So I'm going to talk about some operations that would define what a Q is. So let's talk about this. So let me list out the operations. So Q. So remember, this is an ADT, just like a stack is. So it's a container. That follows. I'll get rid of the parentheses. I'll say FIFO, or first in, first out, insertion, and removal of objects. It is an ADT that supports the following operations. So let me list out these operations. Colon. Let's put a colon here. Makes things a lot more fun. So the first one, this is going to look very similar to the list I had for the stack, just a heads up. So I'm going to have NQ. It's going to take in an element. It just says insert the element E at the rear of the Q. So that's what NQ is. Then we have DQ. So you're going to see that NQ and DQ are very closely related to push and pop. That's the first thing I really want you to notice, is that DQ is just going to be if the Q is not empty. If the Q is not empty, remove the element E. E at the front of the Q, and return it. And otherwise return null. Because if the Q is empty, we don't have anything that we can DQ. Now, you might say, Dan, what's the peak of a Q? I'm just going to refer to it as front. So when I'm taking a peek at the front of the Q, I'm just going to examine my friend. Don't do this for your friends, by the way. It's not very nice to pick them up and lift them and inspect them like that. I'm sure that's a very normal human relationship that people have, right? This is a joke, obviously. But anyways, so return the element at the front of the Q, and null if the Q is empty. So very similar, same idea, except I'm just not going to remove it from the Q. I'm just going to inspect the front of the Q. I'm just going to inspect it. So just if say my friend here is just sitting here at the front of the Q, my job is just to inspect. I'm not going to take my friend away from the front. I don't think my friend would like that. Unless they're really waiting. In that case, I don't know. So we have size. This is just like the way we defined it for a stack. Return the number of elements in the queue. And of course, we have is empty. So is empty. We're going to return false if there is at least one. If there is at least one element in the queue. And true if the queue is empty. Now, when I say this, it has 0 elements, just to be very clear, because somebody might say, Dan, if you're saying the queue is empty, I should return this, but you defined it as is empty, right? So it's usually good practice not to define things in terms of literally the words I use. That's just a good writing practice. Sorry, 0 elements. There's no elements in the queue. But yeah, these are all the operations for the queue. So I'm going to start off with what I would argue is the simpler of the two implementations. I'm going to start off with the linked queue. So it's okay if I head over here. So just to reiterate, I have enqueue, dequeue, front, size, and is empty. So most of these are the exact same. It's just now the queue has different rules to it than the stack does. Just slightly different. So that naturally means that the implementations I'm going to use are not very much different. So let's head over here. Okay, that way, not this way. We're not going up that way. So you're going to see that I'm just going to be repeating a lot of things I said earlier. So I'm going to go a little faster because I think everybody here sort of has a grip over the representation of these things. The second implementation, I'm going to have to be a bit careful about this. So one implementation that you can use, this is one way you can represent a queue, is a linked queue. So this is one of several ways you can represent a queue. This is just one of the ways. So I'll tell you up front that the setup is similar to the linked stack. So it will have it has a counter, so it has count. But it's going to have something that's a little different. So in our stack, we took and kept track of the head of the linked list. So naturally, like if you see my picture I had here just previously, does anybody have any suggestions of what maybe I should, like, is there something else I should hang on to or keep track of with my linked list? Think of the picture I drew just previously on the board over here. Think of that picture with the line. Yeah, the rear. Perfect. So a very natural way to think about this is to include that. But both the head and tail, some people call the tail the trailer, but I'm going to call it the tail. The head and tail of the linked list are kept track of. For the front and rear, respectively. So I need to hang on to these two things. Now, depending on how much time we have, I might show you a very clever way you can get around with having these 2 pointers. You can actually do this all with 1 pointer if you set up the queue a little bit differently. So just be very careful when we're talking about this, because keep in mind, this is still a linked list where I have a data and a next attribute. So we have to be a bit wary about this. So when I'm doing this, we'll still have the count. Now, let me draw. I feel like the best way I could do this is just showing you how it works. So I'm going to draw some fun pictures, because I think that's usually the easiest way to kind of see it. So what I'm going to do is I'm going to initially start off with an empty queue. So I'm going to start off with an empty queue. So remember in the link stack, I had it where top was pointing at null, and I had a count that was 0, right? But now I'm going to have, instead of top, I'm going to call it front, and I'm also going to have rear. So I'm going to have front and rear, and I'm going to maintain a count, just like my link stack implementation. So right now, this is what the initial setup of the data structure would look like. So far, we're doing okay. So this is actually the exact same setup I had for link stack, except we just didn't have rear. So what I'm going to do is I'm going to perform some enqueue operations. So just to make this a little easier for us to see, I'm going to kind of a visualization of this queue. So I'm going to have this being the rear and this being the front. And to make this a little easier for me to see, I'm just going to have some squares here just to make it a little easier for me to see and for you to inspect. But keep in mind that it's just a line. Whatever's the leftmost spot closest to the front, that is the front. So I'm going to just start off by, I'm going to enqueue. I'm going to enqueue an element called A. So what I do here, I have to perform an insertion into the linked list. But you have to keep in mind, I have to hang on to the front and the rear in the appropriate way, right? So I have to make sure I update these appropriately. So at the beginning, I know that front is equal to rear, which is equal to null, right? So when I do this enqueue procedure, I'm just going to draw it here. So this is the initial setup. So let's draw it out over here. So I would have, A, where front and rear are both going to be pointing at my new node that I created. See, nothing too exciting quite yet, right? Nothing too exciting. Remember, all I have is this extra rear that I have to keep an eye on. Yeah. So anyways. Now, suppose I do another enqueue. Suppose I enqueue B. So where should B go? Does it go before A or does it come after A? Any ideas? Yeah, after A, right? Because remember, this is the rear. It's coming in this side. It's not coming from the top or the front. It's coming from the rear. So naturally, when I do this, you have to be a bit careful. So I'm going to create a new node. I create a new node. So I'm going to have my new node here. I'm going to have B. Now, it's a brand new node. It's at the rear. So most certainly, I'm not going to have anything yet after this. So because I have access to the rear at this time, what I can do is I can figure out, okay, so it's very similar. It's actually quite analogous to what I did when I was doing push operations, except now I'm operating on the back. Does everybody see that? So what I'm going to do now is I'm going to take advantage of that I have the rear here. So I can use this, because it's pointing here, to tell me to update the next of this node, which is the rear. I tell its next to be the new node, and then I update rear. So rear is now going to point at this node. And of course, I update count. So now count. So keep in mind, count now is 2. I forgot to write when it was 1 here. So now, does everybody get the general idea of this? So when I do another NQ operation, if I do C here, the same idea. I'm going to create a brand new node. Its data is going to be C. It starts off where the next for this is null. I have rear so I can figure out what exactly I need to assign this to be because I have this when I create it. So I'm going to tell it to, hey, look, the next node's going to be the new one, and I'm going to update rear to be pointing at the node that has C in it. So are there any questions at all so far about NQ? Does this seem pretty natural? It's just like when I was doing push, except instead of from the front, now I'm just gonna put them on the rear like that. It's just the other way. Thank you. Don't forget to update count. Yep. So you guys are pros at this. I like it. So of course, if I could do another NQ, and I could have, of course, another node on here, and I would update the pointer just like before. Now, question. If I wanted to do a DQ operation, what should I do? Can somebody tell me? Any ideas? So, I'll give you a tip. It's very similar to something we've seen before. Yeah, so it's just like when I removed the head of the linked list, what we call top. Exactly. This should look like, it's like, yeah, no, that's the same thing we did before, right? So all I need to do now is I need to remove this, and I'm just going to return, remember I got to return this. So I need to make sure I hang on to this. I update front to be this one. I get rid of all of this. And I'm done, right? Wait, I have to decrement my count. Don't forget we have to decrement the count. Now, there's one thing you have to be a bit careful about. Yeah, so we have to move front to be perfect. Now, one thing we have to be very careful about here. What happens if it's... Do we have to worry at all about rear over there? Because rear is definitely pointing at a node, right? Do we have to do anything with rear? No, right? If I DQ, say for example, if I DQ B here, notice that it's just going to be pointing at the front is going to eventually meet up with rear again. So my only stress, the only thing I'm going to stress here is just be careful what front and rear are. In fact, I even make a note of this in the notes, just to be a little meta with you, is that I literally say, what do I say here? This is fun. I'm just having a little bit of fun here with you guys. See, I'm being dramatic here. So I literally say, just to be dramatic for you, update the front and rear as per the removal appropriately. So that's something that I think everybody sort of has a grasp over, but I just wanted to remind you of that. Yes, it just always changes from the front of it. That's the big thing I need you to remember about the queue. It's very similar to what we did before, but just remember the way we insert and remove from this container. Very good, very good. Size? Somebody tell me how do I implement size? Yeah, it's just sitting right here, right? I just return count. Is empty, same idea as we had before. Like I said, it's very nice. And if I ever want the front, I just return whatever the data is in the node for front. Isn't this lovely? It's like you're just relearning the same thing again with just a slight tweak of the rules. So now, this is where the fun comes in, is I'm going to show you another implementation of a queue. And now, you're going to run into a little bit of a problem with our array-based version of a queue. So let's head over here, and I want to present you an interesting conundrum that we're going to run into that I'm going to show you how to resolve. And it's going to be a little, if you've never seen this idea before, it's a very handy one to keep in mind if you ever are really picky about memory. So naturally, I showed you the link version first, so that means that this array-based one is going to be a little trickier. But I can assure you its algorithms are very simple too. It's just that it's a conceptual leap mostly. Now, one thing I will make a remark of, it's in the notes, is that you can actually implement a linked list version of a queue using just a single pointer. It's so-called a circular linked list. I have a description of it in the notes. I'll ask you to just take a peek at that, okay? It's a really neat way of doing this same process, so you don't have to have a rear and a front. You could just hang on to the rear and you just modify the structure of the queue so that you point at the front. It's a little interesting. But let's talk about this last one here. So it's called a circular array queue. So I'm going to present you a very interesting situation based on what we've seen with the array-based version of a stack. So same idea I'm going to have before. So I'm going to have a very similar setup. So suppose that we used the exact same idea we had from before. The same one that we had at the beginning. If I were to enqueue, where would be a natural place for me to stick it? So, yeah, position 0, right? You'd put it right here. And the great thing is that you can use the exact same ideas that I had before, except now instead you can have a front and a rear, and these are going to keep track specifically of the positions in the array. And we're going to have a different variable for counting. So we're going to actually have a count. So this is because the front and the rear actually play a somewhat different role than they did in our stack-based implementation. Here it's literally going to be that the front is position 0, and the rear, for example, here would be wherever the next position needs to be. So in this case, you'll notice that I'm just going to increase front by 1, or rear by 1 appropriately whenever I need to tell you where the rear is versus where the front is. So in this case, I have one element, and the rear currently is sitting right here, right? This is the front, so if ever I need to dequeue, where do I have to access? So for example, if front is 0 right now, I just have to access. So if I need to dequeue, so remember it's from the front, right? So if I call this array queue, that's just the name I'm giving it, what position would I need to grab the element from if I'm dequeuing? From front, exactly. So if ever I need to dequeue, I just look at the front. Whenever I need to enqueue, so if ever I need the enqueue, and I've been seeing it in the chat, it's at rear, right? So if ever I need to enqueue, I just inspect the spot where it's in rear, and I would just simply increase the counter to keep track of the number of elements. So I must stress that in this version of this, we don't actually want to keep track of the number of elements using front and rear. We could, but it makes things a little bit more complicated than we need them to be. So now, I want to present a weird conundrum to you, and we're going to leave it on this conundrum. So what we're going to do is suppose that I did a whole bunch of enqueue operations. So whenever I enqueue, I put it on the rear. And suppose I do a whole bunch of dequeue operations. Now notice, every time I do a dequeue operation, it's this one, right? So I would increase the front by 1. I could dequeue again. Keep in mind, I'm not keeping track of the count right now. If I dequeue that, I get 2. And so on. So notice that this will just simply increase front. But what's happening with all of these elements here? Am I using this space at all? Like, is this being wasted right now? So suppose I want to do a whole bunch of NQs again. Suppose I want to go NQ, NQ. I might run out of space in my array if I know I have n elements at all times, the capital N for my capacity. So what would be nice is if I can use this space here. So that brings me to talking about, so you could implement conceivably an array-based queue using this idea that I presented, but you notice you're going to waste a lot of space here. So yes, that's one suggestion. Somebody is pointing out, should we move every element to the, so like we could like, if I get your suggestion right, you're suggesting we shuffle them over so like it all shifts over like this, back over to the front? Yeah, one by one? Yeah, that would work. But I would like a very effective way so I don't have to really do that. So I keep things very simple, just like I had before. So one way we could do this is we can use what is called modular arithmetic. So you may have seen of something called mod. You may know as integer remainder. What you could do is you could bend this whole structure. So this is going to be weird at first, if you've never seen this idea before, is you can bend this array into a ring where this is position 0, this is position 1, this is position 2, this is position 3, and so on, all the way around to position n minus 1. And you can look at the array more like a ring if you use so-called modular arithmetic and you use the mod operator. Not sure if anybody's seen this operator before, but what I'm going to do is I'm going to stop right here. And notice one thing I want to point out here is that if you take my idea where you could just keep NQing and you could keep going, what if you can make it so it comes back around and starts over here again? That's what this is going to achieve. So for the purposes of today, what I'm going to do is I'm going to stop right here. I'm going to ask you to take a look at the circular array queue in the notes. And when we come back, we're going to start talking about sorting, okay? So we'll stop right here. I apologize for going a little longer here. So that being said, I want to say thank you very much and have yourself a beautiful day. I'll see you later.